Hey everybody, it's Susan Linder, your host of the Innovation Storyteller show. I love bringing to this show cutting edge developments in fields that you typically wouldn't learn about in your day-to-day life. And talking with Dr. Blumenschein is a highlight of that. Let me give you a little bit of background on Dr. Laura Blumenschein, who is an assistant professor of mechanical engineering at Purdue University. She received her PhD in mechanical engineering from Stanford back in 2019 and is supervised by Professor Allison Okamura. Her research focuses on creating more robust and adaptable soft robots that are inspired by plants. These grow to explore their environments and build structures and soft haptic devices, which allow for more seamless human-robot interaction. Laura is an NSF graduate research fellow and an MIT TR Innovator under 35. And I came across Dr. Laura from this list of breakthrough researchers at MIT. And I'm just so thrilled to have you on the show today. Laura, thank you so much for joining me.
Well, thank you for inviting me on. It's really exciting to always broaden sort of my audience that I can talk to about the exciting things that are going on in, robotics and soft robotics and what we're doing. So I'm always excited to have conversations like this.
And there's nothing more exciting than two women talking about soft touch robots. Like I can't think of a more exciting way to start my Friday morning. So, so let's get into it because, can we just get started like a little bit earlier back, like childhood? When did you start developing a passion for mechanical engineering as a young woman, as a little girl? When did that all come to you?
Oh, that's an excellent question. Well, so as just a start, I have to, thank my parents for being two wonderful engineers, right? So both of my parents were engineers. My dad was a mechanical engineer. My mom was an industrial engineer. And so there was always this feeling of engineering as like a thing in our household when I was growing up. And what that meant was, I did all sorts of activities, as a middle schooler, high schooler, elementary age kid, that just played around with like putting things together, making interesting contraptions. One of my favorite things I can look at as like when I really figured out like engineering might be a thing that I want to do long term. It was for some club and we had to build a mousetrap vehicle. So mousetraps powering the vehicle, and it had to go out a certain distance and come back. And just that little extra challenge of it has to come back to you at the end leads to so much more interesting engineering, work that has to go in. So, solving problems like that as a kid, even if they were kind of, small, not as important problems, really led me to where I am now. Yeah.
Yeah, it's funny that return trip issue is so important. I saw, I'm on a Facebook group called America's Slow Decline into Cultural Idiocy. And one of it included a pamphlet from a national park that said, put in your canoe, note, river does not come back. Like you must actually find transportation when you get out of the river. I was like, yeah, yep. That coming back mechanism, for a mechanical standpoint is a reminder also for us.
Oh, yes. Thinking ahead as an engineer is always important, right?
Always important. Always important. So you pursued your career at Stanford, not too shabby a spot to be surrounded by really brilliant minds in engineering at Stanford. And then how did you come across this concept, or was your mentor, Allison, was she already working on this?
Yeah, so it had, I describe to people sometimes like it's like I caught the last seat on a rocket ship, where I came to Stanford, I came to work for Allison Okamura about, I would say, a month after they sort of discovered this idea and they were playing around with it. And so she said, why don't you work on this? I don't have anything else for you to do right now. We'll figure out later what you're going to do long term. Just work on this for a little while. I don't know if it's going to go anywhere. That was sort of the idea.
And when you get the
Yeah.
plan to work on this, how did you conceive it at the time? How was it explained to you? And maybe you can
Yeah.
explain for
So
our audience what it is exactly.
yeah. So how it was explained to me at the start was, uh, we've got this new type of actuator. So actuator meaning, something that takes in energy and puts out motion in some sort of way. And this actuator being different, new in the way that instead of, rotating or sliding along like you might see with like a crane, or you can think of your car wheels as like actuators. This was extending, and it was extending, from the end, and doing this by essentially what we call everting. Everting is kind of a word that exists, but we also sort of made it up. But the idea of reversing this material inversion, so that you can get more material out at the end. And that was where it stood at that point. It was like this idea of like, it kind of acts like a plant. We're thinking of it as plant inspired, but we don't know what to do with it yet, right? We just know that it's interesting because it's different from anything else that really exists.
Right.
And
And for
so,
my
yeah.
audience who's listening, right? I mean, you're thinking about, consider that like time-lapse photography where you see a shoot that's coming out of the soil and it's slowly uncoiling and it's kind of extending its way into the sun, right? Pursuing that
Yeah.
forward motion, that forward movement. And to get a robot that is soft-sided, right, that can actually begin to propel itself and to extend itself is something that's really critical in tight spaces. And tell us some of
Yes.
the applications as you envisioned it, just so we can get a mental picture while we're talking about it.
Yeah, fantastic. As you described it, yeah, it's very much like a plant in that it's kind of pushing itself into the environment. And the important bit of that is that it doesn't have to move. So plants don't have to move to get through their environment. They grow instead. And so
Mm.
what happens when you have a robot that can do that, or some sort of autonomous system? Well, that means that suddenly you don't care about what your environment looks like. So where before, let's say we tried to get a little driving robot to maybe swim underneath some glue. I don't know why we need a robot to swim underneath some glue, but like we need it to get down there. It's going to get stuck almost instantly. The viscosity of the fluid, everything like that is going to stop it. And you have to kind of cleverly design your robot to interact with the environment correctly. We're kind of ignoring all of that when we talk about growth, in that the robot can use its own body, its own structure to do all of that. So it doesn't have to push against anything. And, a lot of the stuff we looked at early on were kind of these cute demonstrations where it grew into a bath of glue. It grew through sticky mouse traps, right? Things like that. But that's emblematic of the things we actually want to do with it, right? We want it to go into locations that other robots can't access, maybe because they're too slippery, they're too sticky, they're too tight, right? And these are all places where if you have to think about, normal animal locomotion, animal-like locomotion, you have to worry about what is your environment going to look like. And we can kind of set that aside, which is fantastic if you're going into unknown locations, like a search and rescue situation where you don't know what's happened inside of that building, or an underground tunnel that's built by ancient civilizations that no one's seen in thousands of years. You don't know what it's going to look like inside of there, so you have to kind of be prepared for anything. And then interestingly enough, maybe we know a little bit more about the inside of the human body, but it's still very useful in there where we're not applying forces to the environment because of how we grow. And so we can make more comfortable procedures, less dangerous procedures, if we can build something that grows in the human body, instead of kind of pushing into the human body. Yeah.
Fantastic. And I mean, the applications across industrial spheres seems endless, right?
Yes.
I'm thinking about like, even like an oil rig where, a bolt potentially needs to be tightened, or some piece of debris needs to be removed from a place that's really critical that could be causing a huge issue. Tight little spaces, a very narrow corridors, right, where something needs to be extended and pulled out or pushed through if something is clogged.
Yeah, so pipes and oil is a perfect example. Yeah, we have to get to somewhere and we have to do something at that spot, like pull up some piece of debris. Or if you've ever seen the inside of an airplane wing, you might think of it as just a bunch of empty space, but it's actually this very tight lattice of structures and equipment and everything like that. So that's another space where really it's not big enough for like a human to get in, but maybe we want to go check to make sure that that bolt didn't come out of place, or that piece of equipment is properly positioned after we put together the whole wing. And we can't really do that very easily right now. So all of these sort of spaces where we're building this intricate machinery, if we want to look at it after the fact, we need something to be able to get in there.
Yeah. So where did this idea arise from? And, as you've been building it, tell us what have been some of the bumps along the way?
Yeah, no, that's a great question. And I think this is really an interesting type of answer for a question like that, which is like many things in innovation, the idea came from trying to solve a different problem.
Oh, so tell us about that. Yeah.
Yes. So the problem that we were working on at that time was trying to get a super long extension actuator for things like essentially like human-like robots, like doing muscle actuation and stuff like that. You're sometimes limited by how far your actuator contracts.
Wait, so let's use some of these words. So like a muscle actuator, for example, could be like a gripper, right? Could be
yeah. Or it could be something where maybe you make like a human-like robot, right? It has like an arm, but you need something to actually make the elbow move. And so you put something between the lower arm and the upper arm, and you need that to kind of shorten in order to pull your arm together.
Right.
And so that was sort of what we were trying to do, was like make something that's analogous to like a human muscle. And turns out this is not actually very good for this. It doesn't really work that well that way, just because of kind of how the forces are applied in the direction. There's a little bit of technical, things there. But like the important thing is that even though this doesn't work for that original problem, figuring out this like very interesting extending structure meant that suddenly we were faced with this, okay, this doesn't solve what, we were faced with this idea of this doesn't solve what we were trying to set out. But this is so interesting. It's like piqued our curiosity. And so those early times when we were working on that, and if you want to talk about bumps along the way, I think that early curiosity is one of those initial bumps to get over, where you have to ask the right questions so you can figure out what something like this might be good for. So we were just sort of sitting there saying, well, what does this mean? What if we try to go really fast? How fast can we go? What if we try to go really far? How far can we grow? What if we try to go through very narrow gaps? How narrow can we go through? And it was this process of trying to figure out the right questions to ask so that we could figure out what can we actually do with this and what direction can we push it. And I think that, it's not as obvious a bump maybe to some people along the way, but being able to expand your curiosity and not sort of be limited by your initial preconceptions of something like that is really important, so that you don't get stuck assuming things that aren't actually true. So the quickest example I will give of that is early on, we were making ones that were maybe 2 or 3 feet long, right? And so it would grow out about 2 feet, and we'd do interesting things with it. And we're like, okay, so that's how that works. And it wasn't until we said, wait a minute, how far could we actually grow this thing? And I sat in the lab and I was like, yeah.
When you did those initial experiments with the 2 feet long, what kind of things were you doing?
We were doing things like we were like, what if we tried to grow it through a small gap? What if we tried to put it through mouse traps, or sticky mouse traps? If you've ever stuck your foot on one of those sticky mouse traps, you know what I'm talking about. And so we were looking at some of the same things that we had been talking about, like this not moving, growing instead. But like we weren't really hitting at like some of the really amazing things that we could do. We were still thinking about it as an actuator not as a robot system, if that makes sense.
I see.
And so it wasn't until I remember very clearly, there was one day when I was sitting there and I was like, what if I just made one that was like 30 feet long? Let's see what happens. Let's see if it can do that. With no sort of trying to be clever about it. I'm just going to make one that's 30 feet long. And so I did, and I snaked it. I grew it out. It went all the way across our lab into where the office space was, and like snuck under someone's desk and popped up next to them and gave them a nice surprise. And it did it very easily. And I said, oh, okay, I guess that wasn't ambitious enough. Maybe I should try, let's just say 300 feet. Let's go a full football field, right? And then, I had to be a little clever, like, how do you get 300 feet of material so that you can grow it out? But it's same sort of thing of like, when we tried it, it worked. And there's this great video clip that I still love sharing of, we grew this 300-foot long robot, and I'm walking back along it, taking a video along the entire way. You get back to the beginning, and all of my lab mates, you can see all of their feet there, just standing, wondering at this structure that we have just grown out. Because again, it was this very like curiosity-driven exploration at the start there.
So that then leads to a whole different question around, let's say, okay, we want to build this thing. How did you settle on materials?
Yeah, so materials is an incredibly important problem here as well, where we were looking at easy to acquire materials early on. We had plastics, something called low density polyethylene. It's basically, if you've ever had a plastic bag that has, cereal inside of it or some other thing, some other food product, you probably run into LDPE.
Okay.
But you can acquire a lot of it pretty cheaply. So that's what we were concerned with at first. And then after that, we started to look at other materials. So we looked at fabrics that are used for things like camping, tarps for camping, things like that. Turns out those are pretty airtight. We need it to be airtight. And they're a lot more resilient, so our robots don't break as fast. And that was sort of our journey of, we went from, these early robots where they were really prototypes and kind of disposable to, we were like, well, we don't want to be making new robots all the time. Let's move towards more robust systems. And then as a result, also, we started to move from, we're just going to do this in the lab, we basically had a tube that came out of the wall and it had pressurized air. And then we had to say, okay, what if we wanted to take this outside and put it into, a mining tunnel, put it into a search and rescue situation? How would we actually go about doing that? And so we set out on the process of figuring out, how do we kind of make a unit that we can take out with all of its electronics, all of its, air supply, everything like that, so that we can take it out into the world. Yeah.
Wow, because that, there's a durability factor, there's a pliability factor, right? In thinking about all of these things. And
Yeah.
sourcing is important too, but for the moment, you're just at the point of, does it work, right?
Yes. Yeah.
And figuring that out. So what was the first application? I don't even know if we're at application layer yet, but what was the next right step you took once you figured out the materials?
Yeah. So again, like you're kind of saying, it's not quite at like application, like commercialization, but we did sort of get, I think applications are a good way to push forward technology like this. And so the next step we took was, we were approached by one of the next steps we took, we were approached by a professor of archaeology at Stanford, who took these yearly trips to this dig site in Peru, where he would explore these essentially air ducts, ancient air ducts that were used by pre-Incan civilizations. We don't know why they used them, but they did build them. And they find like
air went through them as opposed to some other liquid.
Probably.
Uh-huh.
I don't know a ton about the construction of these buildings, but I think that's their theory right now. But they do find like pieces of broken pottery in them, or they use these air ducts to find other rooms. So it's like if you can follow it, you can figure out where another room to dig up is. So you're not just kind of excavating everything, right? And so they wanted a robot that could tell them where, what was inside of these tunnels. And so that was really the point where we started to solve that problem of what if we have to take this out into the middle of Peru for a week and it can't break, or at least it can't break so much that we can't fix it there. So it has to be at least durable enough that, once it breaks, we can pretty easily fix it. And so that's where you'll see this a lot in kind of commercialization of engineering technology. We started doing things like lifetime tests. So we said, instead of just working it as long as we normally would do for research, we're going to set up the robot and we're going to make it do 100 cycles of behavior. So it grows out and returns and grows out and returns and grows out and returns. So we make sure that if it does that 100 times, it doesn't break. And so we did that for kind of our steering technology that allows it to change the direction of growth. We did that for growth. We did that for our chamber that we're using to hold a lot of the electronics until we were pretty satisfied we could take it to Peru and have it work the entire time. Yeah.
Fantastic. I mean, I'm thinking about like that little demonstration you see at IKEA, where they're like smashing a chair cushion, endless time.
Yeah, exactly.
To make sure it doesn't die when you're in the field. And, as an anthropologist who's been on a bunch of digs, the thought of being out in the middle of nowhere and going like, and scene, like we're done here.
Yep.
There's nothing you can do about it.
Yep.
So how did that go? And, I also have this desire, as you're talking about it, to like stick a camera on top of that and, make sure you're doing. So tell us how that worked out.
Yeah, so one of my colleagues, Margaret Code, took the robot out. She was the one who actually got selected to go to Peru. And so she collected these fantastic videos of managed to get the robot to run through 3 different tunnels down there over the course of a week. And figured out, this one takes a right bend at about this location, this one goes up a wall, and this one just kind of continues straight ahead. And it's the small things that I think, if you are outside of this problem, don't immediately come to mind as like the problems you run into. But we were up against, there was another team down there with a little wheeled robot. It was basically an RC car with a camera strapped on. And that car would drive in and then it would run into a rock and then it couldn't go any further. And so the really nice thing was our robot would grow in and run into that rock, and kind of like a plant root, trying to grow down into soil, or like a tree branch that, comes up against your house and kind of curves around it, right? It moved around the rock and just kept going. And so it was this really nice kind of natural behavior. Eventually we went on to study that behavior so we could quantify it. But at that time, it was just this nice, like natural response that we had noticed that meant this wouldn't get stuck where other things would. So yeah, we have a series of videos with, camera tip looking into the environment, getting a little scuffed up because it's running into rocks, but, getting us these pretty good videos of what's inside of those tunnels. Yeah.
Fantastic. And just out of curiosity, how did you and the archaeologists team up? Like, so much on the show, we talk about moving cross silos. I don't even know how that chocolate and peanut butter combination comes together, that the archaeologists are talking to the mechanical engineers about this.
Yeah. And this is one of those things where I think it's hard to force it, but honestly, it's the publicity you get from, putting your work out into wider environments. What I think had happened, I do remember kind of the sequence of events, but what if I had to guess, one of the students of this archaeologist saw our video we had produced for Stanford, kind of advertising the robot early on when we had some of our initial publications. And they had the idea, looking at our system, hey, what if we put that into our dig site? And so it's this interesting thing of like, we never would have thought to approach them. And that's happened multiple times over the course of our kind of lifespan of this project. Of someone will approach us and say, hey, can we use your thing for X? We saw it, we think that it could work for this. And the really tough part early on, I think even now is, and this is where I'd love to kind of push the technology forward, is they'll come to us and they say, how do I make one? And we say, it looks easy, but it's actually not that easy. And unfortunately, like, we're going to have to work with you to make it work
The answer
for
is
your
no.
specific application.
We do it. Right?
Yeah. And it's like, I wish I could just tell someone, and we're getting towards the point where I can just tell someone, you can just make it yourself. But especially when we're talking about these new areas and these new applications, it takes a little bit of that expertise, or at least that experience with the system, to be like, here's what it can do, here's what it can't do, and here's how we change it. So originally those students came to us and they said, how do we build one to take to Peru? And we said, I don't think we could teach you how to build one and also have you build it, in the 3 months before you want to go to Peru.
Oh my God.
Right. Yeah, exactly. But maybe if we work on it for 3 months, we'll have a system that we can take to Peru with you and that we can, use. And I was saying multiple times this has happened. So we were also approached by some ecologists. So people, studying animal behaviors at Stanford, who were studying this endangered species of salamander that lives in the lake at Stanford. One of the dried up lakes, I guess, technically. The lake's not there anymore. It's a lake bed now. And they wanted similarly to use our device to kind of put a camera inside of these animal burrows and understand, is there a salamander in there or not? Very simple question, but actually is like a pretty hard problem. And so, yeah, we worked with them. That was towards the end of my time at Stanford, but that was also a fun kind of experience of someone else seeing our technology and saying, hey, I think I know what this could be good for, right?
Fascinating. And it's the reason why I so often encourage academics and scientists to talk to popular mediums like mine, right? I'm talking to chief innovation officers and innovation teams around the world from all different disciplines and industries. And nothing would shock me less than someone going, oh my gosh, we need that for our bakery related products over at, Hain Healthy Foods, or, Campbell Soup, going, gosh, that extruder, that tomato rice soup extruder, the rice always gets stuck in that thing, and we really need a robot to go in there and unclog the rice.
And those are the moments that just absolutely fascinate me, because, right, I think right now people have this conception of what robots can do and what robots are good for. Robots are just, you take a human and you take them out of the system, and then you put a robot that looks like a human in, and it does all this stuff. But I think that we could do so much more, right? With, especially with soft robot systems where we're working with these materials. And it's those moments where we've pushed the technology far enough that we can show interesting things. And someone comes along and says, I've never thought a robot could be good for this, but I think your robot could be good for this. And that I find incredibly both exciting and just fascinating as a problem to solve.
And to your point, I don't think a lot of my listeners, so I certainly don't, never think about robots in soft materials. When you were explaining earlier about the contraction of the human arm, right? We think about a robotic arm, but we don't think about the soft tissue on our bodies that would be contracting as tendons and ligaments and muscle fiber that go back and forth. And to your point, we're always trying to replace that human robot with something that looks like, C-3PO, right?
Yeah, we're like Terminator, right?
Or Terminator, right? But there is a wealth to be learned from the plant kingdom that far extends beyond the human kingdom, right? Which is a pretty narrow set of, it's a pretty fantastic robot, the human body, but the plant kingdom certainly has just as much to teach us, if not exponentially more, for all of its myriad forms.
And I'm certainly not saying that humanoid robots are, not good for anything, right? Because we've built our world to be used by humans. So there's a lot of problems where you need a robot that looks like a human to do the thing that humans are already doing. But for all the things that humans can't do, we need to figure out, like, why can't they do them right now? If it's like, I can't look inside an animal burrow, right? I can't stick my hand in one, usually it's too long. And so it's
Or dangerous
that,
if I'm
too
having a
dangerous.
tarantula or what have you.
Yeah. Certainly that as well, especially if we were talking about oil rigs earlier. I certainly would not want to go into an oil rig, try to crawl inside of the pipe of an oil rig if someone asked me to fix something inside of it. So yeah, so it's these things where either as kind of a civilization, we have sort of given up on solving these problems. We've just accepted that they're problems, or we haven't figured out yet how to solve them in specific ways, or in efficient ways, where, as you're saying, taking inspiration from these natural systems that already exist and can already do these very interesting behaviors, I think is really important. And plants don't just grow; they do incredible things, very slowly. But it's, you can think of, like, a plant doesn't have a brain, but if you have a Venus flytrap, it knows when a fly that is the right size lands on its open mouth, and it'll close and it will eat that fly. So how does a thing without a brain do that? And there's a lot of chemical and mechanical systems inside of the plant that help with that. And it's really a fascinating area of this crossover between biology and engineering. Yeah.
Well, not to mention, right, that mechanism that's snapping shut. I mean, we think about the mousetrap as the most fundamental method of, something, opening and closing, maybe like a door hinge. But, applying those plant structures to a robot. And, we haven't even talked about the haptics of it, which is part of the discussion in your bio. But I mean, it's just amazing to me how, I feel like I am becoming the robot every time my Apple Watch goes, stand, breathe, walk, I'm like, yes, sir. Like I'm some
being
kind of
told how to be human. Yeah.
Right, exactly. I'm like, I'm just, and I'm following orders and I'm doing it, and I'm like,
yeah,
is the robot here? Like I am being, yeah. And a friend of mine who is a phenomenal speaker, she gave a talk at a conference we were at in Amsterdam called the Next Web. And she got on stage and she was talking about the human robot interaction. And part of it was when robots first came out, and certainly voice-enabled robots like Siri and AI, and even just speaking into the telephone when we used to ask, 411 for someone's like a restaurant name and to get the phone number back in olden days. She would describe it, when she was doing her research, as people would talk to Siri like Siri so that Siri could understand us. And we would emulate being a robot in the hopes that the robot would understand us better. And meanwhile, the programmers are trying desperately to get the robot to understand every iteration of the human voice, every accent, every nuance of language. And yet we are thinking we have to talk like this, like it's just...
Yes, this is it's a little tangential to the growing robot stuff, but this is also an area that I am incredibly fascinated. And I think most people who work in soft robotics care about how humans and robot interact, because one of the things about soft robots is, if it runs into me, it's not going to hurt me, right? It's generally pretty soft and it's not going to injure me. Unlike if you've ever seen robots that work in like automobile factories making cars, you don't get anywhere near that thing. It's going to bowl you over, and like it's a huge safety hazard.
Right.
And so, I am incredibly interested as well by how do humans who are coming up against robots think about robots? And as a result, how should we design robots to get, we're not trying to trick people into how they think about it, but we're trying to elicit certain, certain behaviors or certain responses in the same way that, if you want to go to a fancy party and you want everyone to think of you as belonging there, you put on fancy clothes. It's the same thing. It's like we should dress up our robots in certain ways or make them act in certain ways such that the human reads the right social cues off of our robot. So in the area of haptics, we're looking at, not exactly like how the robot dresses, but can the robot tell you something by, changing its like pattern of bubbles so that when you touch it, it feels different. And so, maybe you can understand this robot is calm and this robot is upset, however we kind of want to communicate the information that's going on. Yeah.
So if you could envision your next great application, what's the dream? What's the dream of how you'd want to see the robot used next? If you could, Laura, what would that look like?
Yeah. So with the growing robot, one of the things that I am really thinking about right now is not just the fact that it can get somewhere, but the fact that it kind of grows and builds a structure along the way. So my dream kind of going forward is this idea of a robot that can build something you need on demand and quickly, right? So you come across a gap and you need to get to the other side. You program in a few things, you press a button, and the robot grows out and builds you a bridge, right? Or you're going into a search and rescue situation. Yeah, this would be fantastic if we could achieve it, right? You're going into a search and rescue situation and you need to shore up some rubble so that humans can get inside. And so you put in a few dimensions, you grow the robot out, and it builds, an on-demand lattice. Maybe it's not going to be as strong as like, building a traditional structure, but if we can get it to the point where that structure is usable for transporting things, for doing force applications, supporting things, I think that's the next direction I want to see for some of this growing robot work. Is it's not just about getting to a place, it's what you do with the structure you build along the way, whether it's helping, now we can get air, food, water through that tube wherever we need it to go, or other robots maybe, or we do something physical with the structure. I think that's really fascinating.
Well, I wish you continued success with this fantastic robot, but I have some hot seat questions for you.
Sure.
Okay, so a question that I ask on the show often is, what do you think is the greatest invention, the greatest innovation of all time?
Oh, that's a fantastic question. Wow. I think really when it comes down to it, we can look at kind of very early automation technology. So things like, the early cotton mills and things like that. Like those are the first steps where we're taking this idea of a machine can do something that a human used to do, or a non-living thing can do something that a human used to do. And so I think like early automation, early stuff like that, maybe it's not the greatest invention anymore, but it's certainly the thing that has propelled us forward the most into our modern era.
Okay. And it's a collective too, right? It's not even completed just for one person. This is like on a mass scale. So fascinating. I don't think anyone's ever shared something like that before. If you could be on any innovation team in human history, which team would you have liked to have been on?
So there are I worked briefly with a team at NASA that I was not working on this, but they were working on Robonaut. I don't know if you're familiar with Robonaut. It is a robot astronaut. And so they were focused on trying to put a robot up into space. If I could kind of rewind time and not work on soft robotics, not work on the stuff that I'm working on right now, I think that would be fantastic to kind of be in that innovation team, this idea of putting some robots into space for the first time ever.
Wow. And I mean, the pictures from the Webb telescope,
Yes,
they're just mind blowing and I can't stop staring at them. And I was listening to the engineer who was working on it, and he was kind of the project manager. That was his very humble way of describing his work there. I'm just a project manager. And he said there are 241 single point of failure errors possible in the first 2 weeks of deployment. And that means one error would shut down the entire mission.
Yes.
So 241 of those episodes anticipated in the first 2 weeks.
Yep.
And he said probably the most stressful 2 weeks of his life, because his team had to conquer all 241 of those in the process of it. And as it turns out, Webb is actually is producing images better than they had ever anticipated. It was just mind-numbing to hear that.
Yes, science, like science instruments that go up into space are so fascinating, because it's just this unique engineering challenge of, once you put it into the environment, you can't touch it anymore, or it's very, very difficult to get back at it. So yeah, engineering teams like that, I think, are just operating on a very different level that I think is wonderful. And I would love to learn, some of those skills as well.
Amen. Okay. And finally, what's something that drives you crazy, or that you wish you had a deep, deep desire to see connected that has not been created yet?
Yes, this is a great question. I'll go back to one of my standard answers, which is, so I think that sci-fi books and like things like that, technology and sci-fi and movies about sci-fi, show interesting and amazing things that we could do, but they also make our robotic job as roboticists a little difficult, because at one point in time I was working on a robot that like is wearable by humans, and so it helps you move, and everyone just said, so when do we get Iron Man? And I said, oh, hold your horses, right? We are so far from that. We can't even get, I show videos of robots trying to open doors and falling over, right? And it's like, that's where we're at right now. So if I had to pick out a pet peeve, it's this weird disconnect between where we're actually at and what we're actually capable of, and how exciting that is. Even that robot that can't open the door is super exciting to me, and what people actually want you to be able to do for it to be exciting. I wish there was an easier way to tell people how exciting the stuff we're already working on is, without them wanting us to already make Iron Man. Yeah.
Well, goodness knows what's happening at the Department of Defense.
Maybe, yes, you never know.
That thing is already in a closet somewhere, I guess.
That's true.
Dr. Laura Blumenschein, thank you so much for joining me on Innovation Storytellers today. If people want to follow your research, Laura, what's the best way for them to do that?
A great question. So they can, look up my lab page. It's the RAD Lab, RAAD lab at Purdue. So I believe it's engineering.edu or engineering.purdue.edu/RAD Lab. You can also, follow me on LinkedIn if you want to find me there. And that's about it, I think.
Fantastic. Dr. Laura Blumenschein from Purdue University, thank you so much for joining me today on the Innovation Storyteller Show.
Thank you as well. Thanks for having me on.